Testing 1, 2. Alright. Need a little bit higher in the levels there. Hi. How you doing? It's nice to see you again. Pandemic hair getting more pandemic-y. Ugh. Gotta do something with it though. It's getting out of control. But yeah. I figure I'm just hacking. I don't know. It's kind of fun having long hair. I've never had long hair in my life before, so there you go. True story. Okay, what to work on today? Probably Rosby, right? Although, I don't know. I heard Advent of Code is coming up. I don't know. I get why people like it. I usually try it. I get like 3 or 4 puzzles in, maybe 5, and I'm like, ah. Like 1 puzzle every single day is, even if it's just for a month, I don't know. For some reason I just can't keep it up. But I'm tempted again to try it once more. Sounds like we're going to be doing a lot of networking this year. This could be fun. So I'm tempted to just try and work on like getting set up for AOC, creating a little Haskell projects, maybe a little helper utility library or 2, just to get us started. Maybe. Maybe we should just do an AOC problem or 2 from last year. Anyways, I'm still on the fence about it. I don't know if I really want to do this. Rosby, I'm kind of in the same place too. Like we did last week, zippers. Right, so we worked pretty hard on making sure that, going back to the fundamentals, you know, making sure we kind of really felt like we understood zippers, and maybe we just gotta go back and just do it, you know. So let's go on down with Ros. Let's just do Rosby. Don't feel pressure to turn it up. Folder. Rosby. Why don't we bring up another fun thing that I didn't anticipate. So working a full-time job on Haskell, in Haskell, and then doing a Haskell stream at night. It's a lot of Haskell. But it's a good thing. Because we love Haskell, don't we? Bow, be tree. We also need a new one for zipper merge. Yeah, we know what to do. Cool. My voice is a little bit. I'm reading my kid's Bone, and I liked it. It's a comic book series. graphic novel, and I really like doing voices for all the different characters. Oh boy, dad problems. Okay, what do we do? We have some unstage changes from last time. Like random. Not sure why. We have those. Oh, right, because we did zip tree stuff. That's kind of like a separate file. Yeah, that's right. I didn't really commit this or anything. Cool. So I think it's probably safe to get rid of that some of that stuff. I'll leave it there for a minute. What I want to look at is the actual B-tree implementation that we have been working on. Right. So we started merge. We have undefined the others case. I was thinking there might be a way, a different way to do merge. It might work for the others case. Other than, see, in this code we're trying to find a key index that we're going to insert at, and into the node that we're trying to merge with, and then using that. I guess the idea is that we have an insert childs function that tries to use that key index to figure out where in the vector to insert the two children we got from the split of the leaf from below. And oops. One idea I thought might be interesting to do this, to make this code a little bit tighter and smaller, potentially, is to merge it all together and split it apart as we go. What I mean is that if I could just get this to work today, that would be great. Maybe not spill anything, that would be good. Okay. Sorry, we have two nodes that we're trying to merge, right? One is a vector of keys. There's another vector of children, child nodes. What we're trying to merge in looks kind of like this. Okay. These might be. Actually, yeah, no. Let's just do it like this one, just like the other one. All right, so it might look like this. Got one single vector here. Right, this might be like, I don't know, 6. And this might be 3, 10, and 22. Okay. And, whatever the values, these are all child values, right? So, one of the invariants we have to maintain is the order invariant. I think we might be able to use that in our merge operation. So instead of trying to figure out what index 6 would get inserted into, let's say 1, we return a new vector with 6 inserted at that index and the 1, which is sort of what we're doing in this code over here, this line here. And then trying to figure out where we should insert the children smaller than 6, you know, in that key where it should go based on that index. What if instead we just combine the 2 vectors and sort it? Okay. That would bring the keys together. Right, so it'd be 3, 6, 10, 22. And then we do the same thing with the child nodes. Right, so that maintains our order invariant on the keys, and we just have to do the same thing for the children to make sure that the child nodes are in the proper place. Right, and what does that operation look like? Right? Well, I think essentially we would have one big vector of all our elements. Okay. And I think we would still have them. Well, here's the tricky part of it. The B tree itself. The B tree thing here. No. So a vector of trees and a vector of Ks. So this is supposed to be one element bigger than keys. Right, so that this node, here is a node that contains all of the keys less than 3. This node here contains all the keys that include 3 and anything greater. So we have a vector of all of the keys. We can group them into a constructor based on these elements here. And so we'd have some operation like take, but looking at the value instead of just taking a certain number. Like a higher order take. Take the value equal to, say, 3. Or less than 3. And I would take all the values from this giant index that are less than 3 and apply it to the appropriate constructor. Say, no, well, this is going to be leaves. I think it's supposed to be like maybe leave or whatever. And that would become 1. And then we take the next one based off of this, so anything less than this value, then anything less than this value, then anything less than this value. And then what's remaining becomes the last element. And I think that we would end up with maintaining at least the order invariant that way, assuming that this is sorted. And the only thing I'm concerned now about is what constructor, how do we know which constructor to call? And so we're just splitting, we can split nodes as well. And we don't just split leaves, although that's kind of like our first use case. So we won't If it's leaves, it's one thing. If it's other nodes, we won't know. We will have that. I think that information, won't we? Because the type of this thing here and the type of the children would be. They would have that node constructor with it. Potentially, or it could get really mixed up. It could be B nodes or B leaves. So, just a thought for that. Let's see if we can we can convince GHC and ourselves that that's roughly speaking correct. Hey Barry, how's it going? Coworker, eh? Did you start this week, Barry, or is that coming up? And hello, Swarm Collective. Altern? Altern? Hopefully I got that right. Sorry I wasn't checking chat there for a second, but sometimes I like to ramble. When you get me going. Whoa. Hard to make it stop. Okay, so what would that kind of... Let's just do it down here. That merge function. Merge tree look like? Right, what would its type be? I'm gonna get a B tree, K of E. I'm gonna B tree, K of E. We're gonna get and back a merged B tree, K of E. Yeah. So we call the first one like tree new. Three something. Okay. Well, I don't know if this function needs to handle the case where it doesn't need to really know about overflow, it just needs to know about merging trees. And it can violate. I think it's fine. This is going to be an internal function, so it could violate the invariant in our tree. Super deep thoughts. I might not be in super deep thoughts later though, because energy is like, oof. Tired today. That's okay. Sometimes I get jazzed doing these streams, so we'll see. Merge tree, yeah. So I think it can temporarily, at least, violate our invariant that these nodes need to be only have a certain number of keys and things like that. Or basically, violate the order invariant temporarily. Like this, we just want to merge the two. That's all I want to do with these functions. So, in that case, we've got quite a number of possibilities to cover here. There's 2 inhabitants here and 2 inhabitants here, making what, like 4? Yeah, 2 times 2 is 4 combinations. So we're gonna have a B node. Well, technically we also know that this B node, it's always going to be a B node on the left side as the first parameter for this helper function. So there's keys and childs. So we might actually be able to narrow this down. All right, we can't really merge with a leaf. It just doesn't make sense in the algorithm. So So we're going to run into, what else we're going to run into with this function is invalid patterns, or incomplete patterns. So let's just head that off. I guess with, so we can't merge with leaf, so the other case, we just return the 2. Doesn't make sense. I think that makes sense. Okay. So what do we got in scope here? Oh yes, that's not quite right. Yeah, we're pulling apart the B node at this level, aren't we? So that's not keys, it's actually the order, which we don't really care about. Here, we just want to merge through these, so this would be a node. Keys, trials. And that's better. So I want those vector of childs in there. And vector of keys. Don't care about that. We'll do the same thing on this side as well. Okay. So I have the vector key, parent keys, the parent, and the keys that we're trying to merge. Those merge keys, merge childs. Okay. Pull that over a little bit to the left column. Is that still valid Haskell syntax? Okay, good. All right. So then we kind of wanted to merge the keys together. Merge keys in the parent key to the parent keys into a new sorted vector. We have to have an OR constraint on K in order to order on keys. K, the vector K. I think we got vector sort. That should be a thing, right? So let's get. I'm just going to bind it for now in a let. Although we might get rid of it. Towards keys. We're gonna do something with that. We're gonna do vector. Is it append? I think that might be the definition, if I'm not mistaken. Yeah, it's not append, it's cons? No. Ugh. What was it called again? Concat? It's probably concat. List of vectors. Alright. Or plus plus. Yeah, no. Nerd. Skadoosh. No, you don't like that, do you? Okay, fine. I'll put it back the way it was, and I'll just use the dollar signs. That's what's going on. Yeah, super stylish, super sloppy Haskell hacking here. That's what we're all about sometimes. Just got to get it going. Okay, I've got a function hole here that takes a vector and wants to return a C. So, why do I got a function here? 46. That's weird. Maybe I'm doing something stupid. What's going on? It's not kind of not what I was expecting. All right, fine. Let's do it like this. Does that change anything? Now you're mad at me because... How is that even a thing? Did I mistake? No, you're... Is it a weird thing with qualified names and operators? That can't be it. Because I feel like you put plus in there, that's going to override with list prelude. Still got a function type there, though. That's... Oh, well, no. I guess that kind of makes sense. Yeah. I guess. So what we want to do is now we want to sort that. Yeah. Sort function. So how do you sort vectors? Or is this the wrong data structure for that? Something else that works on lists. That's not right. Try data sequences, maybe. Huh. Okay. No sorting vectors for you. Transform it to a list. I guess. And then sort the list and then transform it back to a vector again. Great. It's dirty, but I guess whatever. Let's go for it. To list. Okay. Import data.list. Sort that. Get it back to v.list. Gotta do what you gotta do. Okay. So we got the keys. Sort of keys means what we need to group or split together somehow our values of our children, the keys of our children. This is kind of where we might need to branch to two cases here. The two cases being we either have a vector of B nodes, or we have a vector of B leaves. It's really it's kind of the two vectors we would expect in our data structure. Case of node. Keys. Case of leaves we have map of key values. Maybe not be so straightforward as I had hoped, but maybe it will be. Who knows? Who knows? Okay, so in the case where we have a list of our vector of leaves as our B leaves as our nodes, let's just is there a way for us to even a way for us to split as a part of that point? Like just gather the leaves together and know that they're all leaves, because the vector doesn't really tell us, does it? It could be a vector of either. It's no good. Type doesn't tell us. Like, I don't think we can pattern match on this type parameter to vector. Right? Pretty sure we can. Exactly what I want to do, though. What do we do? Like, that's a tough one. I don't know what to do here, actually. I'm kind of stuck now. How can we pull out... How do we even know to pull out the lists of leaves, or if we can pull out this? We should be pulling out a list of B nodes. There's just no way for us to tell. Is there? Is there a way for us to merge on the value? No. Ah, dang. Okay. Might be a dead end. That's a nice thought. Maybe we can pick something up that we didn't find. Let's just comment it. Maybe there's something about that approach we can still use though. So in this merge operation here, this doesn't really need... Maybe this approach is pretty good after all. Yeah, Swarm, we're working on merging the children. And I feel like I'm a little bit stuck on that because the children are of type B tree, which is a sum type. The two constructors are B node and our B leaf. Here. And we just have a vector of them. Now, technically, when we're merging a node, conceptually, like when we're talking about the B plus tree in this operation, we're either be merging because we split from a leaf. So we have a B node that we're merging with leaves as the node children, like just B leaves. Unless we did something really wrong, but it should be just B leaves. Or we're merging because we split from another B node. And so the children will be other B nodes. Does that make sense? So when I got down to this idea of merging merge childs and parent childs, their types, like I can't, at least I don't think I can pattern match on their types. Maybe I don't know something here. Like what I got in scope here are a vector of either one or the other, but I don't think I have a way of telling which ones I need. It'd be one thing if like I had some information in this in scope that would let me say, okay, I'm merging from a split leaf, or if I'm merging from a split node. But I don't see anything that tells me that yet. Like when we're talking about a vector of B tree KV, we have to handle a vector of can be a complete mix of the two. So, yeah. Kind of a dead end. I mean, we could, like, I don't know, hackily search the vector, right? But then we'd be like on traversing the whole vector to see if, okay, we only encountered B node, so it must be a B node. Or we could even just look at the head, maybe, and discriminate on the head value, and just assume that they're homogeneous. It's kind of hacky, but it could work. Yeah. Yeah, that's true. Well, I guess we could probably do that's probably enough information. Let's just look at the head of the vector, and we can discriminate on that. And choose the appropriate way to merge the things. Okay, let's see where it leads us. Thanks for the rubber duck there, buddy. Friend. Case vector.head. Merge childs. Doesn't really matter which one we pick. Actually, let's get toads keys and toads childs, which can just be keys. Sorry, merge childs with parent childs. Can I extract them into, yeah, separately based on their constructors? There's probably a way to do that. Maybe with traverse or with lenses. But technically, in the algorithm, we would only expect a homogeneous vector, one or the other. So it's this might be a case of like using the wrong data structure, like vectors aren't expressive enough for our use case. Maybe there's a better type for them, but I don't want to write. Or maybe we could new type something over vectors that would help us. I'm going to keep that thought in mind. Let's keep that thought in mind, because maybe that might be something. I don't know if we could, maybe not a new type, but maybe there's a simple type over vectors we could do to provide that information to our algorithm. Or maybe just homogeneous vectors somehow. Homogeneous vectors from a subtype or something. I don't know, something crazy. Totally not crazy. I keep something a little bit zany. Maybe little wild. Okay, so we can look at the heads of the total list of childs. What do we get? I don't know if that's even safe. We could probably assume this will never not be safe. But those are famous last words, aren't they? Yeah, so we either have a B node. We don't really care. Or we have a B leaf. And again, we don't really care. Right order, whatever. That gives us our case split. In a very hacky way. But if we know that the head of our totally merged child's vector, and we assume that the vectors are homogeneous so that they're not mixed with B nodes or B leaves, but they're just B nodes. That's kind of what we have to assume here. Expect that it's like documentation. Yeah, so then from here, we know that we're going to construct, well, then we're just going to group the elements together into new nodes, or we're going to have to merge together all of the B nodes, and then follow their values and their This is going to get schwank. Yeah, we're kind of using vectors to emulate M-array trees here. And it's kind of always been a pain in my side. Doing a fixed size tree with a fixed number of children, of course, in Haskell is really straightforward. But yeah, it's not that they, well, it shouldn't technically. I mean, in the structure, the so I keep pressing Emacs key bindings in other windows, thinking I'm back in Emacs. Computers don't work that way. Yeah, so we're just using vectors internally in this data structure to represent the M-ariness of the nodes. They can have any number of a certain number of keys and a certain number of children. These vectors won't necessarily be of the same size either, which is my next problem. I was just thinking about when we're merging nodes. Because just to highlight it a little bit to illustrate the point, the way this kind of looks visually in our heads. It's kind of like this. These would be like the keys, and this would be a vector of other nodes. And this would point here, back there, do I have a function to add a leaf to a node? That's kind of what we worked on that. Actually, hey. So maybe skip over that part and getting ahead of myself here. We're just doing insert right now. we're just inserting the raw key and the value. And the way the insert operation works is pretty tricky. A little bit tricky for Haskell. Because it grows the tree from the bottom upwards, splitting nodes as we go. But that's an interesting point. Okay, so if we had a function that could insert just a leaf into a node, what would that look like? No, let's just write it. KV. Or, no, let's just go lower level now. Let's just go leaf node. Second comment. So, is there system level limit to the number of child leaves? I know what is that to reference. Yes. A B tree is defined by its order, which opposes that limit. So sorry, we're not just technically B trees. We're trying to do B plus trees, but we're just removing the constraint to have the leaf nodes form a linked list at the bottom, at least for now. So yeah, there is a limit to the size of the vectors, and that's determined by the order, and that also tells us when we need to split during the insert operation. What would this look like? There's really only a case we would have to handle. Sorry. We're missing the order information at this level. If I try to do this at the higher level, we would get B tree, KV, which would kind of hide. And then kind of like a weird design decision to take here. Do we do maybe no KV? Because really, we're only interested in doing order, leaf order, leaf, and then you can only insert the leaf into a node. That gets a little, right? And if we don't match exactly that, right, we'd have to return nothing, maybe? We might even need to put a guard in here. We don't try to mix up things. Line 110. Yeah, that's just an example. So if you look at 109, the constructor, we construct an order for the tree. An order 4. These are just an example keys. 3 and 4. No real significance. We're handcrafting this example 1 here. To be, and we take it to be correct, but we're not using the insert to build the tree like our constructor. So. Doesn't mean just Navans. We do something here. And the other thing the other guard we'd have in this case would be like, yeah, if we can't insert a leaf into this node because of the order invariant, right? That's another problem. And the other problem is that depending on the elements of the children of this node, inserting a leaf won't make sense either. I think this isn't really gonna work here. Yeah. Interesting though. So back to where we were. Where were we? What insert with? What was this to do with insert with? What's used here? Right. Yes, this is sort of like keeping, so if we have space to insert, because the size of the values of the leaf is less than the order of the leaf, we need to insert at least one. So we do that by constructing a leaf. That. Otherwise we split the leaf. Values. All the keys are less than K. And we merge up. Okay, yeah. Okay, I think that still makes sense. go to the zipper. No RB leaf would return the inputs. Next, we can't merge into leaves. Merge into nodes. Okay. So we have enough space for children to insert a child. Okay, actually, it's sort of better than that. Otherwise, the otherwise case is we don't have enough space to insert these children. And in that case, I think in the algorithm you're supposed to split the node and merge up again until you don't have to split anymore. Potentially. Yeah. The only case would be if you get to the root node, you can't even split that, and you're kind of boned, I think. Oh, thanks, Swarm. I haven't gotten to algebra E on this yet. Zippers are probably the closest thing we have to an abstraction to help us with this data structure. It's kind of a funny one for Haskell. Again, because of that whole growing up from the leaves kind of thing, you kind of, when you insert, you search all the way down to the bottom, and we only insert at the leaves in a B+ tree. But then you have that overflow thing where if you insert too many keys, the invariant is based on the order, so you have to split the leaves into two, merge up to the parent. If the parent needs to be split again, you got to split that parent, that one, merge it and go up again, and so on and so forth. Like I was saying, you kind of grow it up from the bottom, and it creates a very sparse, wide tree. Yeah, and the idea for that is that at the bottom we're probably going to end up having not necessarily Haskell values like these V's, are probably going to be more like, depending on how you implement the storage engine for this database, probably pointers into compact regions at first. I want to try that. And compact regions are kind of, they're useful in that they can store a ton of data into like a big blob of contiguous memory, but the Haskell runtime, GHC, won't touch anything in that region. It'll just touch the pointer to see if anything still references it, and then whatever. So you get this nice big contiguous region of memory that is untouched by the runtime system. But at the caveat that they have some restrictions on them that might make them kind of slow to update. So we don't want to be holding on too many of these, doing too many updates on these at once. We could also serialize them to disk, so there's the potential for that as well. So we have a really large database, serialize parts of it to database, and we'll bring out the compact regions, deserialize the compact regions that we want as they get referenced, keep them cached for a certain amount of time, that kind of stuff. That's what I want to try. My second backup plan for that is just to use C. Right, write the library for a dynamic allocator of C, and then just use that for file. Because that's what I really want to do. I want to test the limits of what's possible in terms of building databases in Haskell and like addressing off-heap memory. Because there's applications for it. It's a pretty useful thing to have. But I need a B tree. And the audience of the stream has not overwhelmingly, but the majority has voted for us to build our own from scratch as well. So I'm just kind of struggling with it a little bit. Like, I understand it conceptually, but just getting it to work in Haskell, because Haskell it's been a trouble. Oh, thanks for the follow. Much appreciated. Love the follows. Right. So let's move on to, I think we sort of have that going. That branch of it. This otherwise branch, let's try and get rid of some of these undefined before we sign off. Right, so in this case, let's just assume this code is correct. And if we have a case where we have room to insert the child, so we could just insert the child and keep the node, and it's all good. Then, in the otherwise case, we need to do something. We need to split again and move up. Our whole job here at merge is just to merge the node currently hooked to the zipper. Right. And what are we doing with merge up? Well, I think, yeah, moving up the zipper again and calling merge up would be an okay operation to do in merge in this otherwise branch. As long as we're tying things together. So last week we did a stream where we just focused on zippers themselves. And one of my YouTube followers pointed out that we might actually be throwing away our work with the zipper here. So we need to be careful of that and probably write some of those property tests that we wrote last week for this data structure and to test this. You don't know why it took you an hour to remember. That's okay. You know, pandemic times. I'm sure we're all a little scatterbrained. It's all good. I just really appreciate it. That's why I do this. Sort of. Part of the reason why I do this. Okay. Otherwise. We split this node and merge. Do we need a node again? And merge up. How does that look? Bang. That would be... We're not at leaves. Right, so the tree we're looking at in the focus part of the zipper right now has our keys. 12 and 20. And children in this case could be, or in this otherwise branch are going to be other nodes. Right, so these are going to be keys less than 3. Alright, so maybe we have, I don't know, 0, 1. And there's going to be children here that are going to go to leaf nodes. Who knows what they have. Hey, Wizard Stick, welcome back. It's been a while, friend. Pull up a stool. Come check it out. So in this case, say we need to split this guy, this tree here, right? I think this operation is going to be very much like the leaves. We're going to split this in halvesies. We're going to take the mid one, move that up, and then we'll have 2 sub-branches. 3 and all of its stuff, and 20, all of its stuff. And then we have to merge that with the parent that's above here, above this other branch. Okay, so whatever that is, merge again. Kabang. Yeah, I think that's what we're going to do next week. Let's just get this code kind of hacking working, and then next week, man, we're just going to write some property tests for this thing. See if we're getting there. Maybe even just for this, I don't know. We'll do something. Anyways, random thought of the day. So the length of the child's prime vector here is greater than order minus 2. So that means we have room at least for 1. What is it? Order minus 2 is it? This might be not quite right. Oh, that's because we want, after inserting, we want to make sure that it doesn't violate the invariant. That's right. So in this case, in the otherwise case, if we inserted both children that we want to merge with, we would violate again. I have to split up again. So, Storm Collective, yeah, the merge up concept. It is a tiny bit counterintuitive. Yeah, I agree. It hasn't been the easiest concept to grasp either. For me, at least, not how to do it in Haskell. I mean, it's not terribly difficult to understand conceptually, like you're saying. Wikipedia. Well, even the beach plus tree visualizer, we use this a couple times in the stream, just to show. So like a max degree of 4. It kind of grows, adds an element, insert there. It splits because you can't have a node with 4 keys. So if I do 6, it's going to go there, search there, it's going to try and insert it at the leaf. So all the keys have to exist at the leaves, which is why it's a little bit weird. It's going to search again, it's going to split this one because it overflowed. And see how it merged that key up. And that's why it's a little bit strange. Right. there. Right. Now we got a kind of a even number of this stuff. The tree could check this out. One of these is going to split. Whatever we insert. Boop, boop. And if I try to get something to insert over here, that one's going to split, and it's going to cause this one to split. Right? And it just keeps growing. It just keeps growing like that. 40, 43. Right, split there, it's going to split there, it's going to add it up to there. Right. I notice how all the keys are along the bottom too. Everything we inserted. 890, 66, 66, 67. Right. And the other thing is these arrows in a B+ tree implementation form a linked list at the bottom as well. I decided since the operations we're building in this database don't really need it, we're probably going to skip that. We might add it back later, but that's useful for like range queries and things like that, where you need to get a key or get successive keys. You can iterate over the whole database pretty quickly once you get down to a leaf key. So you don't have to like traverse back up and back down, back up and back down. Because especially with a very high degree tree, you can imagine that would be a pretty expensive operation to revisit the same node several times just to get the successor keys. Split. 0 split. And it'll just keep growing. What happens when the root needs to split? We'll keep growing this tree a little bit. Let's go split it there. It's getting harder. Split again one more time. It's going to cause that to split, it's going to cause that to split, and boom! A new root. So this will just keep growing. But it's always from the bottom up. Right, so what we're doing with the zipper, I notice the animation, slow it down a little bit. So we're kind of starting, we're encoding this idea of moving around the tree and remembering where we are in the tree so that when we have to do this operation of splitting, moving back up, moving up, moving up, going down, going down, going down. Just helps us move around the tree. Just along the way, we have to remember that the zipper, currently focused element, needs to be updated and replaced when we move through the zipper so that when we zip back up to the top and we unzip the whole structure, we get a newly built tree with the elements modified the way we wanted them to be modified as we traversed it. So that's the gist of it. It is a bit more tricky to think about than your typical tree data structure. Sure. At least for me. It's been pretty tricky. But learned a lot. It's pretty cool. Yes, the leaves always exist at the same distance. Yeah, so it's balanced by construction. Yeah. And that's kind of the goal. Really useful in databases. Yeah, I know. It might even be like, I'm not sure if Postgres uses a B tree or B plus tree, but it uses one of those as a basic index, if I'm not mistaken, as a default index for a column. So we're going to split this node apart. Into, yeah, where's that visualization? That's all right. Yeah, so we kind of want to take that middle element of our node as key, and then we make the two, then we have two sides. We split it into that. The keys less than the mid node become the subtree of this new node that we just created. And the keys greater than that mid key and all of their children, those become a subtree. And then we merge that up to the next level, I think is how that goes. So how are we going to make subtrees out of this first? I guess we're going to have to construct a new B node. We're going to have to construct a new B node in order to do merge up. And it's going to have one element. Same order. Singleton of our middle key. And the childs are going to be harder to figure out because the vectors are independent of each other. Isn't so key left and partitions by within this key. Presumably, I could maybe use that to. I don't really need the vector. I could just take everything up to. Okay. I have like a higher order than take one vector. I could take values up to a certain amount. Accumulate. take while. Oh, yeah, so that's the vector elements that we would be creating predicate on, which is what we want. Okay, so we can do that. It's the child's. Let's pull that over a little bit. So this would be node. Got this in order. And the keys would be take while. Less than key. Oh, less than middle key. That makes sense. Kind of what we said, right? Fine. And the second element would be the node prime. Drop while. Less than or equal to. So that's our split node, I think. And we need to give the zipper to merge up into. Probably just ourselves, the zipper we're currently focused at. And as long as we define what middle key is, let's just see if we pop something in there. And we're kind of using middle key, the value, so the middle value of our vector. That's going to be have an index. And you have the maybe index. So, now with the maybe in it, we're going to have to do something about that. Value of a. Where's that type checks? Let's just look at this. Oh, you probably want keys as well, don't you? Yeah, I think we're missing the keys. The vector keys and then the vector chocolates. In that case, we want... Does it make sense? How is that even... Take while from keys, not childs. Keys. Something else. Something here. Split up the children. Like we're getting divorced all over again. Divorced. The child of divorce. Yeah, so this is the vector of children. This is the vector of children. Okay, cool. And Z, your problem is... Expected to type a zipper, but... Yeah, actually, I think this is a... tree? Ooh! I got the wrong thing. This is the Z I meant. Or is it? Yes. Okay, cool. So we just have the holes here. We gotta get the children. So, this is where knowing what the middle key's index is, I think, would help us out like it did above. With insert key and insert childs. Because anything that's going to be child of this one is going to be an index that is our index or less than, because the size of these vectors, they have a relationship to one another. Keys are allowed to be order n-1 or order -1. And the childs are the same. At least I want to say the... N, sorry, should be N. Yeah. Sorry, the number of keys you're allowed is n-1, the number of childs you can have is n. And that kind of means like I think that kind of means that if we have, say, the middle value being 4 here, if we map it out visually, we have 4 keys or an order 5 tree, and we pick this element, say, as the middle, arbitrarily. Its index is 1. And the nodes below it can have an index up to, say this is 5. 1, 2, 3, 4, 5. And their indexes would be 0, 1, 2, 3, 4. And so if we were to split this off, we want to end up with this element coming over here. It's going to be going over here like this. Let me just get rid of that buffer and then behind, because it seems to interact with my notes. And that's fine. So we have that, and we're going to make nodes where the keys are going to be less than here. And these two are going to be the greater minimal. So it's going to be the left side, and that's going to be the right side. And now we need to, when we're constructing these here, we need to split up the kids, the children. I shouldn't say that's terrible. Yeah, I'm going to stop that. Child's is bothering me now. Boo. So yeah, we need to cut these up and construct two separate subtrees with these in it. So the value at index 1 in this tree, say it's our mid value, like 3, could be 4, 8, and 12. So 3 is going to come in the middle here, 4 is going to be here, 8 and 12. And that means that in here, each of these nodes this, let me get pink here. This is going to go to that node here. This is going to point to that one. This is going to point to that one. This is going to point to that one, and this is going to point to that one. So if we pick n, we pick 1, then as the new key here, then this node here should have all of the children from our vector from 0 up to 1, including 1. Right? Somehow. But we could just pop them in there because it's just a vector for the children, so that should be fine. Alright, so we got that there. And then we move the rest of these over into here. I think that makes sense. Yeah, and then we merge up zipper with this new tree. Dab. Okay. So that's why I think knowing the index of the middle key that we pick is good to have. So the middle key index would actually be like an int or something. The middle key would be a K. Probably get that out both at once. We have some kind of search over vector. Search, find. We don't want to find just the element, though. We want to find... This will find the index for us. Could we pull out both at once in a tuple? That would be cool. Doesn't look like it. That's okay, whatever. We search twice, we search twice. Let's find index and find. They both return maybe, so it's going to be index. Really, I think merge probably does need to return maybe zipper anyway, so that might end up being fine. In fact, I think a lot of these zipper functions should probably be wrapped with maybes, as we did before. Because once we get to the root, we want to stop. So middle key index is just find index, via find index, where you equal what do you equal? We need to find key index. No. No, we're not looking for an index. That's right, this is the wrong function. What am I talking about? We just need that for middle key. Middle key index, we're just gonna do, length of B. Basically the midpoint. We just do that type 2. And then we use that for getting middle key. That's going to be returned maybe K, which is going to be more. Not going to like that too much. Parser. Of course it's parser. Okay, so then middle key, of course, like we don't have a middle key, we have to deal with that. Because there is no middle key, it's an empty vector, that would be bad. I might just leave that out for now. Just so I can pretend for a little while that I live in a nice universe where dreams are possible. We can have what we want. The other part of the formula, though, is the children. We wanted a new vector that's kind of like the same thing. I think we get a new vector from this. But we don't want to take whiles. We want to inspect the values. We want to just take up to our index. So we get take which takes a certain number, and it might be our index plus 1. Which might just be fine. Middle to index. Yeah, you're upset with me. This is going to get really ugly really fast. I need to give you the vector. I got to give you a second time. Gross. Happy with that. We're running out of time, folks. How fast can I code? How fast can I code? And then we got drop. Hopefully we got a drop. Yeah, we do. Same deal. Okay. I think it's roughly the formula. The only thing we have to deal with is now middle key and the maybiness. But we're out of time for this week. So we're gonna have to leave it as is for now. And I don't know, should I? Well, nobody else is really working on this with me. It's on a private branch, so I'll push the code up even though it's not technically working yet. Generic random, is it tree? I'm gonna kick those out. Gone. Stage that. It. Modify source Rosby for the tree. Work in progress. Handling internals. Just a little reminder for myself. Thanks for coming along for the ride, Swarm Collective and Barry and everybody else. It's been great hiking with you. I love doing these streams, and hopefully we'll see you again next week. I usually stream around this time. Oh, sorry, at 10 after 8 in Eastern time. Yeah, on Tuesdays, generally. Occasionally I've been known to do streams whenever. So if you like what you saw tonight, give a follow and you'll get notifications of those. Otherwise, follow me on Twitter, Agent Ultra, or on GitHub as well. That's where I am. I'm also in the FP Chat Slack, which we've talked about a number of times, but you can find that functional programming Slack. That's me, James King, Agent Ultra. So if you have any questions or you want to chat about anything, hit me up sometime. I love talking about Haskell. I love programming. I love talking about programming. And I'd love to hear what you're working on or what you thought about what we're working on. If you have any ideas for me, that'd be great. Love to hear them. And yeah, take it easy. May your monads always be free. Your types always check. And I don't know, smash that subscribe button and like my stuff. Anyways, take it easy.